Hello everyone, today is day 72 of solving a LeetCode problem every day, and today I'm going to be solving last stone weight. So you're given an array of integer stones where stones I is the weight of the ith stone. We are playing a game with the stones. On each turn we choose the heaviest two stones and smash them together. Suppose the heaviest two stones have a weight x and y with x less than or equal to y. The result of the smash is if x is equal to y, then both stones are destroyed. If x is not equal to y, then the weight of x, the stone weight of x is destroyed, and the stone of weight y has a new weight of y minus x. At the end of the game, there's either 0 stones or 1 stone remaining. The reason why there might be 0 stones is they might both be equal and they both get destroyed. There'd be 1 stone remaining if the two stones have unequal weights. Lastly, it just tells us to return the weight of the last remaining stone. If there are no stones, return 0. So instinctively, it says choose the heaviest two stones. So you're like, okay, maybe we should sort this. But sorting is going to take like n squared time complexity. We don't really want to do that. So what I'm going to do is I'm going to use a heap. I'm going to use a max heap, and basically every time, we can just finding these two largest stones is as simple as just popping the root out of the heap, and that takes log n time. So it's probably going to be more efficient that way. So let's try that approach. So first of all, in Python, I'm going to use a heap queue class, and this represents a min heap. And for us to turn that into a max heap, we know that all the values are going to be positive, so we can just turn all the values negative. So like, for example, we had stones of 1, 5, and 6, and we want to make a max heap. So it's going to be stored as something like maybe this, but we don't want that. We want a max heap. So what if instead we just turned all these values negative? Now suddenly -6 is going to be at the root, but we really know that's just 6. We're just turning the values negative. So in here we're going to say negative s for s in stones. And then next we want to heapify this, so let's do that. That's a linear time operation. Then we say while the length of stones is greater than 1. And the reason why we're doing this is now we want to keep doing whatever this algorithm is until there's either 1 stone left or 0 stones left. So first, it tells us the first things we have to do is find the two heaviest stones. So first stone, second stone. And I mean, like I said earlier, to find these, all we have to do is just pop. So pop from stones, and then the same thing here. And these are log n operations. And then the next thing we're going to do is, so we know that this first stone is always going to have a greater value than the second stone. So what we're going to say is if second stone is less than first stone, then in that case, to the heap, we want to add the value of first minus second. However, I just want to mention something real quick. Remember, we turn these values negative. So really, we want to check if second stone is greater than first stone, since the values are negative and not positive anymore. And so that covers the case of, the two values being unequal. But if the values are equal, we don't have to do anything because we already popped the two stones off the heap. So now those stones are destroyed. We can just leave it as it is. And now at the very end, we're going to return the absolute value of stone 0. The reason why is that this value is going to be negative, so we want to turn it positive. And one last thing that we're going to add is to this list, we're going to append 0. And the reason why is that the last two stones are equal to each other. We'd be left with an array of size 0, which means that stone 0 is going to give us an out of bounds error. So we just want to append the 0 just to cover that case where the array might be empty. If the array isn't empty, it's not going to do anything because whatever values it was at stone 0 originally is going to stay there. Nothing changes. So if I submit this, let's see. So this first, oh, because we want to say first stone minus second stone. Let me submit that now. Cool. So that worked. So let's see. The time complexity of this is going to be n log n, and the reason why is there's n stones, and we're not going to perform n operations. It's going to be more like, I guess, you know, with hold on, let me think about that for a second. So I mean, every time we do something, we have an array of, let's say, like 6, 5, 4, 3, 2, 1, just to make this sorted and be simple. We have 6 and 5, so we'd pop both of those and be left with 1. So we'd go with 1 here. So what I'm trying to say is that I guess we'd be processing n times, because each time we're here, we're either going to remove 1 element or 2 elements from the array. So overall, this is just going to run like n times. And then here we have log n operation. So it's going to be n log n in total. And then as for space complexity, it's going to be O of n. And the reason why is that we have this heap of size n. And yeah, that's my solution for the day.